And I'll also be in the background. Okay.
Okay, hello everyone. We're just waiting a couple of minutes for more people to join, but we'll be starting the webinar soon. Thanks for joining. Okay, well, I think we can start now. Hello everyone. My name is Diego. I am a lecturer at UCL Chemical Engineering, and I'm going to be one of the persons chairing the meeting today. So we are meeting today because we are, I don't know, do you see my screen?
We can't see your screen at the moment. No, not yet.
No? Okay. Can you see it now?
Yes.
All right. Okay. Well, thanks everyone for joining. This is the first event of a webinar series that we are launching here at UCL to showcase what we will be doing in our new campus at UCL East, which is open. Well, it has already opened, but there is a new building opening where our lab will be based, the Manufacturing Futures Lab. So to celebrate that, we have decided to organize a webinar series in which we will showcase some of our research and teaching activities to be done there from this summer onward. So to do that, we have organized 3 webinar series, and the first one is happening today, the nanoscale manufacturing one. But I also encourage you to check the other 2 that we will celebrate in the next weeks, one about digital manufacturing and also another one about nature-inspired manufacturing. If you're interested in joining those, I encourage you to check the link that I just copied there in this slide. And there you will be able to find how to register for them. And with that, I would like to introduce our first speaker for today. So our first presenter will be Manish Tiwari. He's a professor in mechanical engineering here at the University College London. And he's also one of the founding fathers of the Manufacturing Futures Lab. He has been one of the leaders of this effort. And today he will be talking about the research and the teaching that will be done there about nanoscale manufacturing. Manish received his PhD from the University of Illinois at Chicago, then performed a PhD at ETH, where he also became a group leader, and he's now a professor in the Department of Mechanical Engineering at UCL. So without further ado, Manish, the floor is yours.
Thank you very much, Diego, for your kind introduction. I'll start by sharing my screen. So hello, everybody, both panelists as well as attendees. Thank you for giving us your precious time. As Diego mentioned, this activity that we decided to name as Manufacturing Futures Lab started, like many things do everywhere, with a set of plans, and it has evolved to become what it has become. And we thought that we are now ready, because the new campus is coming on board, to do a number of webinars focused around different research activities. And as Diego mentioned, I had the privilege to be involved in this planning, although the founding fathers makes me sound old, which is all right. So what I'll try and do is I will do my best to, first of all, give you all a bit of an overview of what UCL East is, which is a new campus, the biggest expansion in UCL's, University College London's history, investment to the tune of £500 million. And as part of that, Manufacturing Futures Lab, which is where all of us are part of, focuses on, as you would imagine, next generation manufacturing technologies. So I'll start with this presentation here for the next 5-6 minutes or so. I'll give you an overview of what MFL in general is, what are the folks in personnel, and what our aspirations are. And then we'll delve deeper into a second presentation that will focus on nanoscale engineering and science research. So getting into it, as I mentioned, it's a new campus, fairly big, 50,000 square meters for central London. That's pretty big, right? And it's based in Queen Elizabeth Olympic Park, where the Olympics happened. And this was part of government's effort to regenerate the whole area. And now, this is a CAD model. This one right here is the orbit that you might have seen in the slides that Diego was showing as well. And this building, this is a conception diagram, of course. It has now become a reality, and we are now fortunate to have new staff and students beginning to join us as well. And so the time is right to introduce to the world what this is about. Again, very modern, outward-facing, state-of-the-art research facilities, split across 2 buildings at the moment. We call it Marshgate and Pool Street. Pool Street is already operational, up and going. Marshgate is already open for equipment acquisition, etc. So this is all happening. It's not virtual, actually. As you can sense from the laboratory facilities, these are just quick snippets of how the labs are at the moment. This is already about a month ago. So if we see now, it'll already have a number of new pieces of equipment. So MFL in its own is about roughly 15 to 20 million pound investment from the university, and we also have similar quantum of funding, at least through matching grant funding, etc. And this is right at the start, right? So I'm sure it will be growing as we go forward. So a couple of words about what our aspirations are, or what the vision is really. So the thinking was to think about, use the strengths of UCL, which is a lot of which is linked to NHS, patient data, artificial intelligence, and use some of that knowledge to feed into next generation manufacturing research. And as I will begin to show you, this obviously, like many things in research, requires a few disciplines to come together. And if we do that, we start to make impact very clear, both locally, as I mentioned, part of the regeneration process for the Stratford area, which is how the initial investment into these activities came from. But if we innovate and begin to introduce new manufacturing technique, we feel that this should have national as well as global implications as well. And hopefully this will, through this simple schematic, what I'm trying to show is, or what we are trying to show is, we are well set up to go all the way from molecular scale to nanoscale, which is what we will delve deep into today, to device scale, as well as reactor scales. We're doing a series of webinars to hopefully explain to you how this is all embedded in the same set of activity, right? Let me start with a quick example of what I mean. So this is actually a EPSRC funded roughly £2 million project, where we are taking sugar beet pulps, and then we use enzyme catalysis and other catalytic processes to generate monomers and basic chemicals. We then use synthetic chemistry and sustainable approaches to make monomers. We then follow that up using nanotechnology such as high resolution 3D printing, as well as surface engineering techniques to convert them into actual product that hopefully will be creating new applications. So this is an example of going from large scale, to molecular scale, to nano and device scale. And this was not done just by ourselves. A number of industry partners are actively involved in this process. And as we go through, you will probably see a number of project examples that are very similar and go in different sort of directions to feature that. So moving forward, as I mentioned, very interdisciplinary. It, as core activity, Manufacturing Future Lab involves chemical, mechanical engineering, biochemical engineering, as well as chemistry, and in particular, sustainable chemistry. And so all of the researchers and the PIs from these different departments are going to be based and co-located in order to make sure that they can work across and with each other. The activity is organized around what we call research pods, which range all the way from synthetic chemistry, soft materials and manufacturing, to highly intensified, pressure and temperature intensified processing techniques, with laser-based manufacturing, pharmaceuticals manufacture, continuous processing, etc., embedded in between. All of which is, of course, as I mentioned, informed by informatics, data science, modeling, hence knowledge-based. And of course, any research facilities, if it is experimental, will require a lot of process analysis and monitoring and analytics. So we have provisions for that as well. So this is the steering team. Professor Gary Lai is the director of MFL, who's going to be based in MFL in UCL East. And then Professor Gavrilidis, myself, and Professor Helen Hales are part of the steering team. But the real superstars are people that we have managed to actually attract to this new activity. So these are our PIs who work on different aspects, again, to emphasize together. None of the facilities are actually targeted to an individual. These are all shared facilities and shared activities. And these are all underpinned, of course, by 6 different MSc programs listed. The program directors for those here. Of course, the teaching is done by everybody who's involved, as well as the staff based in Bloomsbury. We also have a number of lecturers that are teaching focused, listed them here. And again, we have additional staff from Bloomsbury helping out and supporting these teaching activities. We're also blessed, and this team is going to grow very significantly with technical staff looking after outward-facing activities, industry engagement, the actual nuts and bolts. And I'm a mechanical engineer, so I have to say nuts and bolts. If I was chemical or chemistry focused, I would have sent some sort of molecules and so on. So you're going to have to forgive me for that. So these people are in place. This is going to grow and hopefully help realize the sort of vision that I mentioned to you. This is the last slide on introduction. I want to emphasize that we are very open for business and co-creation and collaboration. This would not have happened if we didn't have the industry partners that we do, and we have mechanisms in place to expand on that further. And that can go all the way from, simple things like supporting our teaching activities, getting engaged there, very easy to do, setting up a PhD project, to all the way to named research facilities where you would like to see something done that is bespoke, specific to your organization, et cetera, et cetera. In other words, we want to listen to you as to how you want to get involved, and then go backwards from that to see how we can facilitate that. Because co-creation is very important for us. It seems to lead to interesting and new things. That is in a snapshot, if you will, briefly what MFL is about. I'm going to take a pause here. I don't know if we have any questions in the chat, etc. And if not, I will shift over to the research presentation. Diego, if that's okay. Do we have any questions?
Yeah. No, not for now. Thanks, Manish, for presenting MFL, the general overview.
Okay.
We don't have any questions for now, but if anyone would like to ask anything, I encourage you to use the Q&A box that you will find on the bottom part of your screen. So we can wait a couple of seconds to see if any questions pop up, and if not, we can move on to the presentation. Oh, I see there is a question.
Sure.
So this question says, you mentioned industrial partnerships. What can you share about some of the projects you have worked with industry with?
Happy to do that. So this sustainable manufacturing grant that I showed you, this came from a previous larger grant where the thinking that was, I was not involved in that. Professor Lai and Professor Helen Hales were involved along with other partners, where they were using bioprocessing and enzyme catalysis, etc., in order to produce these chemicals that can be then valorized. And that led to the follow-on sustainable manufacturing grant that I showed you. So this is one mechanism. The other mechanisms will be to get involved directly in, let's say, shaping some of our manufacturing related MSCs, right? Or bespoke projects, and they can go all the way from, fully funded projects to things like KTP partnerships, to things like Innovate UK grants, and so on and so forth. So there is various mechanisms to enable that, and we put a lot of time and effort to make that as simple as possible and make that as time efficient as possible too, I should say.
Okay, thanks, Manish. There are two more questions.
Sure.
The first one, I think I can answer myself very quickly, because it says, I joined quite late because of tech issues. So what does MFL stand for? So MFL stands for Manufacturing Futures Lab. So that's easy to address. But then the other one is for you, Manish, again. So this person says, hi all, Senior Partnership Manager for Enabling Technology here. I'd like to know which strategic partnership projects are you aiming to set up once MFL has been fully established, and how can professional services help at this stage?
Definitely, thank you for the question, and I'm grateful that you were able to join. So the Sustainable Manufacturing Grant that I showed is one example of how we might be able to progress. We hope that the research trusts, the verticals, which are also very directly linked to some of our MSc programs, will attract at least a few strategic partnerships. And this will become very clear to you when you see some of our MSc programs, because they are actually derived from some of our research. We are going to focus on nanoscale manufacturing or nanotechnology broadly today, but as I showed, we are working across scales, and we have identified 6 different verticals that map onto the MSc program. So those would be good ways to start, for instance. I hope that addresses some of that, Diego, if that's okay.
Yeah, I think so. For now, we don't have any more questions, so I would say we can move to the next part of the talk. Anyway, if people have questions about this part of the talk, they can also ask them later on. So yeah, I think we can move on to the next part.
Sounds good. Thank you very much. So moving on to research, and in particular, the emphasis of today's webinar, which is focused around nanoscale manufacturing. As my title would suggest, I'm heavily involved in techniques of this kind, but what I'm going to show you is going to be a collage of activities where we are not only trying to do the best possible research related to nanotechnology or nanoscale manufacturing, but the thinking is also to think across scales a little bit, so the example of sustainable manufacturing, not only think about how we can make the best 3D printed sensor, miniaturized sensor, but think about how we make them, or to think about what do we make them with, can we, and how does that feed into the whole sustainable ecosystem of manufacturing. And I'm hoping if there is one takeaway message that you go away with, it will be that really from today's presentation, right? So to kick things off, as I mentioned, this will be a series of snippets, basically, of different type of research. So the first one I wanted to get started with, I guess, if you go to a manufacturing webinar and don't hear about 3D printing, there's something missing about that, right? So we do some of the 3D printing as well ourselves, and particularly our emphasis is on high resolution 3D printing. Of course, MFL, Manufacturing Futures Lab, will have a number of commercial 3D printers because we are going to work across scales. But we have bespoke printing systems which are able to do 3D printing with extremely high resolution, going down to sub-micrometer precision. So this one here is a glass nozzle which is extruding out polymer solution using pneumatics, and we call this as direct write printing because the inspiration essentially comes from something that I hope everybody is familiar with, even though we are all digital now, which is fountain pen, right? And then there's the second technique, which is called electrohydrodynamic, where you're applying an electric field to generate little droplets, and you can actually use this to generate 200 nanometer droplets. So, of course, the precision comes through this technique, but one of the major things that we want to use this technique for is for sensors for healthcare. So let me show you a few examples of that as to how we are doing that, right? So this is one first example where we began to print miniaturized pressure sensors on what are called stent grafts that are used in treatment of aneurysms, which is bulging of aorta, the main vessel that comes, draws blood out of heart. And this is a very difficult condition, can be lethal. A lot of research goes into this. So the idea here was, how can we take these devices that are already approved for medical use and make them smarter by adding pressure sensors, for instance. And what high-res printing allows us to do is to do pressure sensitivity with up to an order of magnitude improved sensitivity. Right? And the benefit is you are making the sensor directly on a device. So hopefully that reduces the translational pathway, right? An extension of that is we thought about, okay, if we can do this on stent grafts, we could possibly do this on simple things like surgical gloves themselves, so that the surgeon can wear the glove. And one thing that she can do is she can let's say in the case of labor, when through natural birth process, there are often situations where the baby gets stuck. And the only thing, and this is a time sensitive operation, so the only thing that the midwives or the clinicians need to do is to use haptic feedback to reorient the fetal head. And this is, of course, subject to the training and the skills of the person involved. And if you're trying to do the natural birth delivery in a low resource setting, we thought that by using this kind of pressure or the haptic sensors, we can enable this process to happen better, right? A lot of this activity is based in our WISE Center, which is Wellcome and EPSRC funded center. And of course, that will have collaborative activities bridging over to Manufacturing Future Lab as well. So moving on, these are classic sensors that we have seen so far, right? Which require power sources, but we've also been working around sensors that can potentially power themselves. So an example of that is piezoelectric sensors, which rely on these nanoflowers, molybdenum sulfide nanoflowers. And the beauty is we can make these sensors without using any polling step, which is highly energy saving and wouldn't be possible without nanoscale ingredients being part of the process. This one is another example, which is hydrogel based, slightly different mechanism, triboelectricity here. the benefit here is that this sensor is now self-healing and can stretch itself. And so the thinking, as I said, is how we can generate, the sensors can generate power to power themselves so that we can simplify the design and, enable rapid translation, right? Now, we're not limited to this sort of haptic based technologies or, something that is mechanical stimuli based. So I want to highlight here the work of Dr. Umadisinghu, who is looking at perovskite based solar cells, actually. Again, flexible electronics. This can now take things from miniature sensors to even roll-to-roll technologies, if you want to so do that. So not only you can use these to power sensors, but you could also think about energy harvesting using flexible devices. So very well linked up and feeding into each other and so on. Sensors are not the only things we can do, right? There are other examples. So this is an example that comes from Diego's own work, actually, where he's looking at, I mean, he would be much more eloquent to talk about it, but this is the extent to which I understand it, which is he's looking at recombinant proteins as inspirations, and he's designing these by adding additional material into objects that are multifunctionals. And what that means is you're taking bioinspiration, the best aspects like the silk protein, et cetera, and converting them into multifunctional devices for healthcare, energy, water treatment, and so on and so forth. Really exciting stuff. Again, wouldn't happen if we don't have some of the enabling technology, but stand on its own firm grounds, right? And I'm sure you can sense a lot of nano inspiration in this one as well. Now, so far, I've just shown you examples that are, let's call it hardware-based, right? Experimental. And of course, none of this will be possible without proper underpinning mathematical and computational modeling. So Diego is also looking at, this is an example of simulation work that he's doing, and the characterization using rheometry, for example, where they're looking at all the way from molecular scale. And in some of the research that I'm engaged in, even with DFT, et cetera, to make sure that these designs of the molecules is done in a way that this multifunctionality can be realized in the most effective way possible. We're not the only one to do it. Of course, these are active areas of research, and we collaborate with colleagues all across the world. Absolutely not saying that we are the only ones to do it, but we have our distinct features in the way we are going about doing this, right? So an example of how, let's say, same set of skills can actually have different implications. So if I take you away from, medicine and healthcare application, if I look at it now for metals, so this is a work that Enrique, who's based in my department, is looking at, where he's looking at simulation work, where he's trying to understand how hydrogen embrittlement takes place in metals, for instance. And again, you need multi-scale simulations, you need materials characterization, you need manufacturing capabilities, you need additive manufacturing of the type that we were looking at in order to get to the heart of these problems, which affects a whole slew of applications all the way from infrastructure to transport system. And he's got industry partners directly embedded in his research projects, including folks like Tata Steels and other. Right. So to summarize so far, I'm at the halfway stage. To summarize, what I've tried to communicate, hopefully, is starting from high resolution 3D printing, how flexible electronics is beginning to feed into and simulation activity is beginning to feed into a lot of healthcare and non-healthcare applications. What I'm essentially beating around the bush is to tell you that we are, as most people, scientists on the planet, are motivated by some of the grand challenges. And a lot of the grand challenges that we face are based around energy, healthcare, and water. Now, the difficulty is a number of applications, if they address one issue, they exacerbate the other issue. So, for example, what do I mean? If you look at this chart here that we put together for a proposal, what you see is to produce electricity, we use a lot of water at the moment, right? In other words, in order to sort one issue of energy, we are exacerbating the other issue, which is the water crisis. And this dovetails into multiple applications. There's nothing special about energy and water. This is how, the design or typical engineering has been happening for a very, very long time. Now, in last decade or so, the thinking is to consider these as nexus technologies. And so let's delve a bit deeper into this problem as one such implication. So this is one example, which is led by my colleague, Dr. Martina Michalska, where Martina is interested in thinking about the biological aspects of these problems in particular. And specifically, what she's interested in is how can we engineer interfaces to start to address problems, major problems, such as antimicrobial resistance. And what do I mean by that? So antimicrobial resistance is bacteria or bugs developing resistance to drug. And this is because the dosage is not appropriately controlled. And you can think about, well, what if we could use active material, nanomaterials to address that? And we are doing some of that. But the thinking would be, how can we take that a step further? So we make it difficult for bacteria to adhere to a surface to start with. This will begin to get ourselves away. You can also take and start to think about much more tangible examples, such as catheters, where infection of catheters costs to the NHS on its own about 250 million pounds per year. And of course, if we now start to think about this adhesion issue, we can start to think about things like fouling and so on, right? Which affects, I don't know how many applications. This application is, of course, related to shipping. So for the next few slides, I'm going to show you some examples of surface engineering, okay? And how we can use surface engineering to address some of these problems. And of course, like many things, the implication of that will come from healthcare. So one of the examples of how we are addressing this problem is through our unique capabilities to make nanoparticles, which we can scale up to very large scales, actually, through intensified processing. So this is an example from Max Besenhardt and Professor Gavrilidis' team, where they're looking at gold nanoparticles to achieve these antimicrobial properties. And the beauty here is this is not based on drugs. So the chances of formation of resistance are not there, right? That's the implication here. But let's keep it moving forward. What if we could do this thing slightly differently, in a different way? So the inspiration for this comes from nature, actually. And this is some of the activity that I'm myself directly involved in. And you may be familiar with this, so I apologize if I'm about to waste your 30 seconds. But just in case you are not familiar, right? This is an example of lotus leaf, right, which grows in dirty ponds in tropical climates. And it has this unique property of being able to clean itself because of a hierarchy of surface texture that it maintains. Or this example, which is the cicada insect, which has got this actual nanoscale hair-like structure that also helps with this kind of self-cleaning property, if you will. Or my favorite example, which is butterflies. Butterflies have got two unique properties that come due to their micro and nano structure. So if you put these butterflies underneath the microscope, you will see that their color comes not from the dye, but from the structural property because of the dispersion of light. And they're also self-cleaning. Now, these are beautiful, right? But these butterflies do not need to sit on a plane and go at hundreds of meters per second. So if you want to benefit from this, we need to think in terms of robustness. So one starting example is, let's see how we can use nanotechnology. And so we are very well set up to do that. This is, again, examples of work that comes from Martina, where she is able to design nanostructures across different kinds of aspect ratio and different kinds of form and on different substrates, right? And the interest in polymers is because you can use this not at a wafer scale, 4-inch, 8-inch, 6-inch, and so on, but you can go through roll to roll and make films that can be applied on, large scale windows and so on and so forth. And in MFL, we will have facilities to be able to produce all of this, right? Either directly based on site or through our other user facilities, such as London Center for Nanotechnology. Right, so we can replicate and we can go a step better in terms of creating these structures in a way that we like, and replicate some of the stuff that we were looking at in nature. We can do other unique things, which nature does not require. So for example, again, this is work in collaboration with Professor Papa Constantino from electronics department. Martina collaborated with him, and they developed this technique to make these nanostructures that are very large aspect ratio. And what that enables us to do is to not only manipulate this non-wetting property that I was showing, but optical properties, and in particular, dispersion characteristics and so on. And so one example of that is its use to create materials which can actually radiate heat in a passive way for thermal management, right? So as you can sense, once you have fundamentals nailed down, it's possible to be able to address different set of applications that you're targeting. Okay, I still haven't shown you how this is robust though, okay? So let's think about how this can be made robust. And for that, we need to go back to the butterflies. So let's do that, okay? So this is again an example that comes out from a work from Zurich, right? I was not involved in this, where they did this experiment where they simply took butterfly wings and they impacted water droplets on them. And then what they did is, in one case, they supported the wings, and the other case, they left them free. So as the droplet falls down, the wing is able to flap, okay? What that does, it's able to cushion the blow, which enables the butterflies to take rain droplet impacts that are going up to 10 meters per second. The question is, can we take this an order of magnitude higher? Okay. So as you can guess, we can probably do that, right? So what we did is we used the same inspiration and we developed coating technology, which is flexible. And now you can see here that we can take these coatings to about 35 meters per second. 35 meters per second is roughly your highway speed in the UK, for example, right? And so you can take inspirations and you can take things a step forward. Birds fly, airplanes are inspired by birds, but they can go to Mach 2, that sort of idea, right? And of course, we've tried to understand why this is taking place. And as you can see that the pressure peaks are actually modulated because of the softness of the material that we are able to use. In other words, you're using softness in order to improve the robustness of the material here. Right. Can we do something better using nanotechnology? Turns out we can. And not only we can actually start to address a major problem that this sort of surface engineering has. If you think in terms of, let's say, liquid repellent materials, one of the first thing I hope that comes to mind is these things, right? Non-stick cook pans. These are all made out of Teflon-like materials. And now these have been established to have toxicity issues or biopersistence issues. So what we are trying to do, this is work of Dr. Vikramjit Singh, who is looking at use of metal organic frameworks, which are effectively clusters of metals, let's say or not biohybrid, but hybrid materials that involve both metals as well as inorganic components. And what that allows you to do is to make this nano-engineered surface that has got roughness down to single-digit nanometers, for example. So what that can do is it can help you obtain surfaces that are now optically transparent. And they can resist very low surface tension liquids, because low surface tension means that the liquid can wet things easily. This is why paint generally is made out of solvents and so on and so forth. More importantly, these do not use any fluorinated materials, which means we can do the stuff that we were talking about earlier, but do it in a more sustainable way. Okay. And so we are reasonably excited about it. And of course, all of the works that I'm showing you is not done by one specific person, just the leaders are shown in pictures and so on. So this is my absolute last slide, an example of how we can use one development into multiple applications. So this example is the so-called anti-icing technology. So the same type of surfaces that I showed you earlier, they also offer very low adhesion to ice. So this has implications for aerospace industry. So Airbus, who work with us very closely across multiple different projects, funded a piece of work for us to look at whether we can use some of these MOFs to generate surfaces with very low ice adhesion. Now, you can now begin to see that there is a pattern emerging here, right? The pattern is that we need to think about robustness. We need to think about precision, right? Nanoscale precision, because some of this functionality will simply not come about if we do not have nanoscale precision. And just as importantly, if you nail those two down, and if you can scale these up, then you can start to think about multiple applications. Anti-icing, contamination prevention, reducing fouling, or minimizing growth of bacteria, etc., 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 depending on the application that suits your requirement, right? I think this is about good time to probably stop and maybe start to gather more questions, Diego, if that's okay. So I'll in the interest of time, rather than just to make ourselves go more in the listening mode, get some more questions and see if there is any other interest, I can go into further details, if that's okay.
Yeah, sounds perfect, Manish. Thank you for the presentation. So again, if any of the people in the audience would like to answer a question, please do so in the Q&A and I will read them out. So
thank you.
We can wait
Sure.
a few seconds to see if any questions pop up. Okay, so we have the first question, which says, sounds very promising. Where are these nanostructures having an impact in the real world today? Right.
Very good and fair question, actually, because nanotechnology needs to address this. Because a concern is, are we doing this in the lab through small scale coupons and so on and so forth, and publishing all these good papers that we love to do, right? So there are 2-3 areas where we are beginning to make some real inroads. One example is using this kind of surface treatments. We are working with a number of textile industries where, the jacket I'm wearing probably has a bit of a fluorinated material as well, as do carpets. And as I was saying earlier, toxicity of these materials is a serious issue. So we are using some of our fluorine-free approach and nano-engineered surfaces approach to address all that. So these surfaces are actually being tested by these industries. And we have, as you probably picked up in some of the slides, we filed patents for a number of these. So these will be either translated to potential licensing opportunities, or let's say follow on industry funding to suit a specific set of requirement, etc. So that's one example. The second example is around the fouling issue. As I showed probably you might have picked up this keyboard that was looking a little bit hazy in Professor Gavrilidis's work. And of course, that was a collaboration with Professor Ivan Parkin's team in chemistry, where they looked at coating keyboards and a number of other surfaces and put them in UCLH hospital, because hospital-acquired infections are a major healthcare issue. So this was a part of our impact case study that went in on a couple of occasions. And that problem is very real, actually. And we think that we have some unique advantages in being able to address those. In particular, we now have surfaces which can stop biofouling under flow conditions. Very unique, hot out of press, really, that we should be able to use. The third example, which is looking promising, is we use some of these surfaces to make smart windows, which can actually absorb pollutants. So, imagine your window that is not only maintaining cleanliness, but is able to absorb air pollutants. This will be useful, I hope, in a city like London, where on Oxford Circus, you breach the NOx limit within the first couple of months for the whole year. So there are ideas like that are beginning to make real inroads, actually. And we're fortunate to be able to work with a number of industry partners to be able to enable that. I think a probably good place to stop there, actually.
Yeah, well, I think that gives already a quite nice overview of all the application options in the real world for this kind of research. There is also another question. It's more education related, so I was hesitant either to read it now or wait until the next block, but it basically says, what is the kind of educational background that you need to be involved in this type of R&D?
Right. So I think it's a great point, and I would like to address that, actually. So most of the students that we get, they are not necessarily, from a specific discipline. So this is the reason that we have decided that we need to have colleagues from multiple disciplines working together. Okay, these research pods are not secluded by department. They are not. Most of our students are going to be probably supervised by 2 or 3 different academics across disciplines. Most of my students are that way. So, broad engineering, natural sciences training, STEM training is all we seek, because we don't pretend that a lot of this will be already in your background. If you do, great. If not, we are more than willing to actually train you on the job. That's the attitude we want to take, okay? Because we do realize that there is a fair amount of very deep, chemistry or nanofabrication going on here. It's very unreasonable to expect an MSc student to have experienced all of that. We're not expecting that.
Okay, thank you so much for the answers, Manish. I think then that we are ready to move to the next block. But thank you very much for all the nice presentations. So now I guess I will leave the floor to Martina.
Great, thank you, dear.
Thank you, Manish.
Hello, everyone. I hope you are enjoying the webinar. So we are all staying here till 2:30. So if you have any other related questions to the research part or the first part, please pop it into Q&A, and at the end we will have like maybe a mix of topics. So don't shy out. So I am Martyna Michalska. I'm lecturer in nanomanufacturing, and I'm pleased to introduce Dr. Eral Bele, who is associate professor in mechanical engineering department, and as well as one of our educational programs director called Future Manufacturing and Nanoscale Engineering. And Eral's research is about actually taking some of the natural components, natural materials, to make sustainable materials with special properties to elicit ultra-light weight, for instance. And Eral will now introduce our overview of all the MFL new master programs, with particular attention to the nano engineering one. Eral, the floor is yours.
Great, thanks, Martina. I'll share my screen here so that people can see what I will talk about. All right, everybody. So this, I'm going to introduce the educational programs of MFL. Of course, we have a lot of research going on in there. And as you saw from Manish's presentation, there are 3 departments that are involved, and we have a lot of specialties in the technical background to support this type of research and to really exploit the type of skills that we have there and the types of all the characterization technique that we have there. We also have educational programs. And generally, there is all of the departments are involved in this. And I'll talk here about all of them together. So an overview of the MSc programs that we have. And I will talk specifically about one of them to give an indication about what we are doing with the students there. As I mentioned before, there is several of these programs, and they span a large breadth of technical disciplines. This is an overview of all of them. We have here MSc programs on chemical sustainability, digital manufacturing of advanced materials, stem cell and gene therapies, manufacturing with innovation enterprise, nature-inspired solutions, and future manufacturing in nanoscale engineering. As you can see, they span a large breadth really of manufacturing and have different specialties within this general topic of manufacturing. You can see as well that they cover also aspects like innovation and enterprise in there. They will be taking place at our new campus at UCL East, so brand new labs here, new teaching spaces, custom designed in many cases. And so we have taken advantage of that. Taken advantage that we have space now, that we have new labs, that we have new machinery, new rigs. And I think that it's going to be really enjoyable both to teach these programs, but also from the students' perspective to learn hands-on skill with this new state-of-the-art labs. I'll describe a little bit one of them, as I mentioned before. This is future manufacturing in nanoscale engineering, and it has to do with manufacturing at the nanoscale. What we want to do for the students here is to train them to design, characterize, and manufacture engineering materials. It's essentially a topic that is very applicable, and the field here is growing in industry. So we want essentially to produce students who are industry ready to work in this field. Of course, the field of nanoscale engineering is very broad. We can talk here applications from pharmaceuticals to chemicals and all kinds of things. And here we talk about really engineering materials in this very small scale to have unique mechanical, optical, and thermal properties. And to make this a bit more tangible, right, on something that you can perhaps touch and see and imagine being done, keeping in mind that this is today's technology that we're talking about, but of course we want to train the students for future technologies. Well, some examples are available today are coatings that are structured for color or wettability properties. We're talking here about composite materials tailored from the nano to the micro and the macro scale to have unique mechanical properties. Additive manufacturing is very relevant at the moment, and designing the materials that will create unique structures and unique properties for these additive manufactured parts is very relevant. So we'll teach the students how to custom design materials here. And then we are also teaching them on technologies for precision manufactured components. And then this is traditionally called top-down manufacturing techniques. Just to give you some examples more about what we're talking about, this in the left side, you see some example of a self-cleaning surface. This comes from Manish's group. It's just a demonstration about what the students will be able to both produce and test in the lab. On the right-hand side, you see an example of a lattice. This is a very small lattice in there. 1 millimeter, it's one of the little ligaments in there, and it's designed in such a way that it will have very stiff mechanical properties and super lightweight. And if you can sort of imagine this compressing, you will find out that these little ligaments that you see, they're curved in that way, are designed in such a way that when you compress it, it also shrinks. Okay, so it has what we call auxetic properties. This example here is something that has already been manufactured, so you can see the little imperfections and the flaws that come from the typical additive manufacturing processes. And we'll train the students about designing them, making them, testing them, and seeing how to improve their properties. Okay. Then how does a program structure look like? This is a schematic of it. We have here some modules that are fundamental modules, like fundamental of engineering, characterization techniques. We have micro nano architected materials. Another one is material design for manufacturing. And then the fifth one is precision manufacturing. Now, something that we want to do with these new labs are to train the students to do some hand-on and experiential learning activities. So you see all of these arrows that come from the taught modules feeding into this long group manufacturing challenges module. The idea there is that each one of these technical modules will have a little satellite project that is related to a current challenge that industry is facing at the moment to manufacture materials, structures, and components. Okay, so the students will be working on really manufacturing these the types of structures or materials and improving the manufacturing processes. The last one is the advanced research project, which I will talk about. So just what I want to say with this is that generally all of this educational program has really a fundamental purpose to train students on hands-on skills, so that when they graduate, they are ready really to work in a variety of fields. So looking very quickly at the modules that we'll be teaching, one is on fundamentals of nanoengineering, and this talks about how you design materials in the nanoscale, and it has a practical part on manufacturing technologies in the nanoscale. So the students will actually work with this and create these nanopatterned surfaces, for example. Another one is advanced characterization techniques, and here we train the students on characterizing mechanical properties of materials, characterizing the microstructure and the chemical composition of these things. All of these are practical. There is all of these rigs that we have already, and the students will be trained to use them. Nano and microarchitecture materials has to do with designing and testing composite materials and microlattices. And the practical part of this is looking at the structural testing, mechanical testing, manufacturing of composites, and doing the computational part on finite element analysis. Another module is on material design for manufacturing, and this goes after what I mentioned earlier about custom design materials for additive manufacturing, for example. And the practical part here is computational modeling techniques to design these new materials. And then the last one from the technical modules is precision manufacturing. Here, the students will be trained to use CNC machining to create surfaces here with nanoscale precision. Okay, so all of these modules will now come together into these manufacturing challenges, very practical modules. The students will be working with challenges, will essentially be trying to solve some current and relevant challenges. Some indications are, for example, designing a nanoscale flexoelectric energy harvesting material. Essentially, what this means is that it's a material that will harvest the energy from pressing into creating electricity. Designing 3D printed composites with very high strength. Designing an alloy for additive manufacturing, and fabricating high precision components with subtractive and additive manufacturing. Okay, so all of these will be the little projects that the students will get experience with, and will culminate this module with a community outreach event. The final module here is advanced research projects, where the students will work in teams during the summer, typically, on a variety of projects sponsored both by industry and by our current research activities. There is a suite of elective modules here. As you saw, there were quite a few of these programs within MFL, so the students will be able to collaborate with students from other programs and try to see how things are done really in different types of programs. So I'd like to close with why we are doing this. Of course, we have new facilities, we have new labs and so on, but why are we doing these particular programs? What we want to exploit here is really the opportunity to train the students on hands-on activities. We want these programs to be industry relevant, and we want essentially to produce graduates that will have a broad range of experiences. So they'll be able to use machinery, for example, they'll be able to design engineering components, and they'll be able to test these. And they can apply these really in any field that is of relevance to these types of techniques. So this is the general type of knowledge. And there is also going to be very specialist, very sophisticated knowledge on manufacturing technologies that have to do with the nanoscale engineering. We wanted to do this because we know that this type of technology now is a very rapidly growing field, and there is a need really for students who have the know-how to do this and really have also the vision about what is coming up in the future. So how do you get involved? I saw here the list of participants that we have, a variety of people from students to industry and so on. If you are a student, you can apply to our programs. They are open until the 30th of June. So there is still quite some time to apply for those. And there is a number of studentships and funding opportunities and so on that if you want to know more about, you can contact me directly. From industry, do you have an idea about an R&D project? You can test the water on that very easily. This is a no-cost type of activity, and you'll get the technical expertise of all of our staff, of course, and you will get students who will know what they are doing and who will be trained essentially in this type of challenges that you want to talk about. And there are horizon search projects or manufacturing challenges. We can incorporate those very easily within what we teach here. So this really the point is to get access to work-ready graduates and whom you can enjoy working with. So that's what I wanted to say. This is a good point to stop, perhaps. This is my contact in here. Feel free to contact me about any of these topics that we heard about here. All right, so we'll stop here and we'll take some questions.
Yes, thank you very much, Aral. That was very informative. And I think also what stands out is that, we're dealing with new spaces. We buy state-of-the-art equipment and students will get hands-on experience of those. And so it's really nice and quite unique opportunity to have all of this devoted to, let's say, nano-engineering and other disciplines in the one place. So the floor is open to the questions, not only related to this part, but also to the other parts that we've already heard. So maybe I just start with one question that Manish has kindly typed an answer, but if anyone else is interested and that was noticed, I read it out. So the question was, where could prospective students, researchers find out more about the interdisciplinary research opportunities? So Manish here kindly pasted several links to our websites, and this is to add to it. Will be gradually populating those websites with more details, especially while the equipment is installed, and to give you an idea what we have there, and we'll put more detailed research project. So we can definitely find out more through those websites, as well as Manish mentioned, and Eral before the moment as well shared his email address. You can just contact us directly via email to reach out and explore the potential collaboration opportunities and the involvement opportunities.
This last part is very important, actually, that we are open to all kinds of questions, and people can contact us directly to find out more about these, particularly about new research opportunities. We're happy to answer any of these questions.
Yeah, so there's another question that just appeared. So could you elaborate more on the summer research project mentioned just now? Who are eligible to apply for such opportunity?
Right, so summer projects are typically integrated within the MSCs. So the students of each one of the MSc programs will be involved in these kinds of projects. And so from the students' point of view, this is very straightforward. They will be offered several opportunities to work on summer research projects. And since we are working in a collaborative lab, the nature of the projects will be collaborative as well. From the other part, from people who want to get involved into this project, not as a student, but perhaps as a sponsor, then there is an open door there as well about proposing an idea and having students associated to these types of projects.
Thank you, Aral. Are there any other questions? Please let me have a look into the chat, because sometimes it's the other way. People put things in the chat instead of Q&A, which is fine as well. But it seems nothing in the chat. So any other questions related to our programs, the opportunities, or the research that Manish has nicely laid out? Maybe I will add at this point that that we are moving to the new campus in summer, and this will be open from September, also to public too. So the floors 7 and 8 of the 8th floor building will be with more limited access, because this is where our research laboratories are, but the entire building will be available to public. There will be a lot of events there. So anytime you are in the east part of London, or you want to make a trip to visit the Olympic Park, you are very welcome to come and explore the new site of UCL. So that's available again from September. Any other questions? Not for now. Is there anything else that any of our panelists would like to add to what has been told?
Yes, I guess the one thing to highlight is, as Diego was mentioning, there will be a series of these webinars where we want to, give people opportunities to ask questions about how different things link together and so on. And most of the activities involves almost all of the departments that we were showcasing through a number of presentations that you've seen through. I also appreciate that there may be, a whole lot of information coming your way. So, if you feel that there are aspects that we could do differently and improve, that would, that sort of feedback would also be more than welcome. Please do let us know if, or if there are any bespoke events specific to any area of MFL that we are not organizing, but you would like to see happen, we are happy to do that. That's not a problem at all. And also, I mean, just as a few closing thoughts from my personal side, I would say, is right from the preparation of the slides to let's say planning of the MSCs, this is a joined up team effort. What you're looking at is just one or two people doing the talking. There's an operation behind it. Okay. And so even if one specific person is not able to address a concern that you have, please do flag it, because there will be ways and means to be able to support and enable this. So that's one aspect. And the second is, it is a unique experiment, the Manufacturing Future Lab and UCL East, etc., where we are very decidedly trying to go away from individual specific department, etc., and think about how can we be defined by activities which require multiple skill sets, rather than I'm a mechanical engineer, all I do is break a few I-beams and calculate how their cross-sectional area and moment of inertia, etc., looks like. Not that there is anything wrong with that, nothing. But we enrich that learning opportunity and environment if we expose ourselves to other possibilities and developments. We are not, like I said, unique in attempting to do that, but we have really put time and effort into creating the space that is just inspired by that. So we are not forcing our way, okay, we have 3 people, how do we actually bring them together? The thinking is more from, this is what we would like to achieve, and then we have put resources, including infrastructure, to enable that. In the follow-on webinars, I'm certain you will see the benches as full with equipment. So there's very substantial amount of investment going on as we speak, right? Because the building preparation took time, and it literally involves research all the way from culture, innovation, that's where overlap with some of the museums comes about, to very high precision engineering or sustainable chemistry research, right? So there's a lot there, and we started from there and have gone back to recruit staff to be able to do that. I think by my reckoning, we have staff from certainly from nearly all continents where people live, and definitely we've managed to attract talent from all over the world. And we are very open-minded about that. If all you are listening this for is, I would like to get a job opportunity, etc., do please get in touch. We're very open-minded about this. Yeah. Right, I'll stop there, Martina, Diego, if that's okay. If you have any closing thoughts, more than happy for you to take over, if that's all right.
Yeah, thank you, Manish. I think that the last thing you said was very important. I think this cross-disciplinary team space and the diversity and inclusiveness is what we represent. So this is the environment which is, apart from research and everything, infrastructure, that is great. I think people value the environment and that they're working in. So this is what you can expect, and we practicing it since we got together and working on this project. And from my perspective, it's very enjoyable, and there is plenty of opportunities. So I wanted to have that from my side. Right. So I think you have all the links in this webinar, and then you know how to find us and our website. So please pay attention. We'll be putting more and more information over there, and do attend our next webinars that will be elaborating further our activities. And I think if there is, I can't see any questions. So in the interest of everyone's busy schedules, I think we are close to finish. If anyone else would like to add something, please, welcome. But I guess I don't see any hands up. So I will take this opportunity to thank our speakers and thank you, our audience, for your time and for interest in hearing more and learning more about MFL and these opportunities. And we hope to talk to you soon. And thank you very much. Have a good the rest of your afternoon. Bye.
Thank you.
Yeah, thanks everyone. Bye-bye.
Bye, everybody.
Bye.
Bye.